So we were talking about this. So when n equal to 2, you have xp square. So xpp, that's equal to xp. So this is ih cut, ih cut. So it will be 2 ih cut into p, right? So I mean that, or you can write this as this is equal to n into so ih cut into n into p raised to n minus 1, right? And when so n equal to 3, what you are going to get is ih cut. Yeah, here n equal to 2, what do you get? Ih cut into 2 ih cut into p. That's what you get. When n equal to 3, if you use this formula, you will see that ih cut into 3 ih cut into p square. Okay, that will be the. I mean, so generally you can write x raised to x n is equal to ih cut into n p raised to n minus 1. Okay. That's it. Now, similarly, I mean, you can write. Okay, that's fine. And what do you think? I mean, what about this thing? P x raised to n. Here, I mean, when n equal to 1, you will get just get ih cut, minus ih cut. N equal to 1, you will get p comma x. You will get minus ih cut. When n equal to 2, you are going to get px square. That's equal to pxx. Is equal to px x plus xpx. Is equal to minus ih cut x, right? So so this is equal to, so you can again generalize it as, for n you can write p x raised to n, you will get ih cut x raised to, sorry, ih cut minus ih cut n into sorry, that's will be 2, right? That will be 2 here, minus 2. So minus ih cut n into x raised to n minus 1. All right. Okay. So now once you okay, so let's look at this expression. If you wanted to do this, and so let's suppose that this f of p can be written as a series, summation over n cn p raised to n. Okay, you can write it as a series which involves positive powers of n. N is an infinity. Okay, n is 1 to some infinity, whatever. Okay, so now xi commutator fp, which will be equal to xi fp is cn, summation over n cn p raised to n. Okay, that's equal to summation over n cn comes out, summation over this. Then we have xi p raised to n, which you have already evaluated there. So that is going to be summation over n cn. Okay, so cn into you will get ih cut n into ih cut n into p raised to n minus 1. P raised to ih cut n into p raised to n minus 1. So actually, what is this? This is equal to ih cut comes out. This is equal to ih cut comes out. Then you will have summation over n cn n p raised to n minus 1. And what is that actually? This is nothing. This is f of p. What is f dash of p? That means f dash of p is del pi of f of p. Okay, that is equal to cn into n into p raised to n minus 1, right? So you can write this is equal to ih cut into f dash of p. Okay, so you can clearly write this as ih cut f dash of p. This is one relation. Okay, similarly, if you try to evaluate the second this pi commutator g of x. Okay. Similar, as I said again, I can assume that g of x is equal to summation over n cn x raised to n. So this is equal to this commutator can be written as summation over n cn pi x raised to n, and this is nothing but which is equal to summation over n minus ix cut cn n into x raised to n minus 1. Okay. So which is actually this is equal to minus ix cut into this is actually g prime of x, right? Because g of x is this, g prime of x will be cn n into x raised to n minus 1 summation over n. Okay, so you will get this. So you will get pi g of x which is equal to minus ix cut g prime of x. These two results we use it often. Okay, so just keep it in mind. Okay. Now, let's start. I don't need this. Now, suppose that you have a free particle which is moving with Hamiltonian, which is equal to p square by 2m. Okay, so I mean, as I told you earlier, that I mean, we know this is the classical Hamiltonian. So to get the quantum Hamiltonian, you raise the dynamical. Here you have p, right? You raise it to dynamical. You raise this dynamical variable to operate it. P now it's an operator. Okay, it's operated with p square, and of course this p is Hermitian, so p square p commutes with p, so p square is also Hermitian operator. So this is Hermitian. So this is our Hamiltonian. Okay. So now let's find out what is pi dot. By the Heisenberg equation of motion, is nothing but ih cut into pi comma x. Okay. So this is equal to 1 by ih cut pi 1 by 2m some pk, that's p square, vector p dot, so p square means p dot p, right? So in the next notation I can take it as pk with the Einstein summation convention. Okay, so and of course then you know that p commutes with p, so this is 0, or pi is a constant of motion. Pi dot is 0, so pi is a constant of motion. Pi is a constant of motion. Okay, now let's find what is xi dot. Xi dot. Okay. For xi dot, you have 1 by ix cut into xi x. Okay. So that's equal to 1 by ix cut xi pk by 2m, and that's equal to, and 2m comes out, so 2m ix cut xi commutator pk, and that is equal to 1 by 2m ix cut into this is equal to 2 into this stuff will be, okay, so this will be pi into ix cut. Okay, so ix cut and ix cut gather. So, I mean, see, look at, if you, I mean, you will ask, there will be, what you get, 2 into pk into delta xi pk, that commutator is delta ik. So that makes into ix cut. Okay, ix cut. So that's equal to 2, this will become pi into ix cut, and that's what I put up. 2 pi into ix cut. So I mean ix cut goes away, 2 goes away, you get pi by 2. So you get dx xi dot dxi by dt, which is equal to pi by m. Okay, pi of 0 basically. Okay, now what is xi? Xi you can integrate it, so you will get pi 0 by m. Okay, pi 0 by m into t plus okay, pi 0 by m t plus a constant c. Okay, and now you can find the constant c by taking t equal to if you know that at t equal to 0 xi is xi 0, right? So you can say that so you will get t equal to 0, this term goes away and you will get xi 0 equal to c, or you can say that xi which is equal to pi 0 by m t plus c. Okay, this is xi of t. Okay, xi of t which is equal to pi of 0 by m into t plus c. Okay, now you have to see, look at we know that xi of 0 comma xj of 0 is 0, right? But this is not true when if you see xi of t comma xj of 0. That means the commutator at different times of x's. This is equal to xi of t is basically pi t divided by m, pi t divided by m plus xi of 0. This pi, so I am not writing that, comma xj of 0. xi 0, xj 0, they do commute each other, but pi xi that you will get as minus pi, so you will get 1 by m, t by m actually, t by m into pi xj, that will be minus I h cut, okay, minus I h cut delta ij when I equal to when if you are taking xi of t, xi of 0, then you will get it as minus I t h cut by I minus I t h cut divided by 1. Okay, so you can see that the commutator at different times they don't commute each other. Okay, and now let's look at the we know, in the last module we have seen the generalized uncertainty principle. So if that is the case, we can say that xi delta xi of t square average into delta xi of 0 square average, which is to be greater than or equal to 1 by 4 the commutator AB. So this is equal to, so okay, so modulus of commutator AB square, right? So it will be t square h square by m. So what it says is the following. If you have a particle which is very, if you are talking about free particles, very well localized at t is equal to 0, but that is not true. When at a time t, you can see that you have, the position is not well defined. From here, this expression, you know that the position of the particle is well defined. Right? But when at t not equal to 0, it is very localized, right? But over here, that's not true. Okay, this is not localized. Okay, so now what I'm going to do is the following. So now let's take the general case. The particle is moving in a potential. Okay, particle is moving in a potential of v of x. So your Hamiltonian is equal to t square by 2m plus v of x. And again, there's nothing to, it's a function of x. So now let's evaluate the pi dot. So pi dot is actually equal to commutator pi, comma 1 by 2m pk plus v of x. The first two, this pi commutes to the first term, so that's 0, and so it's just pi v of x. Okay, we will already see in this expression. So that's equal to, oh, of course, that's a 1 by I h cut. 1 by I h cut here, pi dot. So that's equal to 1 by I h cut, 1 by I h cut into 1 by I h cut into this goes away. So what is left with is pi v of x, pi v of x. This 1 by I h is equal to 1 by I h cut into pi v of x is basically minus I h cut into v dot. V dot means del by del x, del pi of del by del xi of v of x. Okay, so you will get your so this will be I h cut goes away. You will get a minus sign here. That's it. There will be a minus sign here. Okay, so you can say that your pi dot, which is equal to pi dot, which is equal to minus or dpi by dt, which is equal to minus del by del xi of p of x. Now let's take dxi by dt. Dx by dt is equal to, again, I mean, it will be equal to 1 by I h cut, 1 by I h cut, p xi commutator pk divided by 2m plus v of x. Okay, so now you can see that xi commute with dx, so that term will not contribute. So you get 1 by I h cut into xi pk divided by 2m, so 2m which will come out, and then you will get 2pi, so into I h cut, 2pi into I h cut. So I h cut goes away, 2 go away, you will get pi by m. Okay, so dxi by dt is pi by m. So what is d square xi by dt square? That is equal to dpi 1 by m into dpi by dt, right? And dpi by dt, which you already know, it's minus del by del x. So you will get minus 1 by m into del by del xi of v of x. Or you can write m into d square xi by dt square is equal to minus del by del xi of v of x. Okay, this is actually, I mean, the quantum version of the Newton's equation of motion. Okay, so now we can just generalize it because it's at xi, right? So you can write this as m into d square x by dt. This is just a component, d square x by dt square is equal to minus grad v. Or these are, I mean, so you can take an expectation value of this minus del v, or m into expectation value of d square x by dt square, you can write it as minus expectation value of del v, and this is known as what's called the Ehrenfest theorem. Okay, what's called the Ehrenfest theorem. Okay, I think I'll stop here. I'll continue in the next class.